Unfortunately, another semester start on Zoom. Hopefully, we will not stay very long on Zoom. This way will go away. And I can tell you at least one of your instructors in this class is in quarantine at the moment. And they will be out by the end of this week. After that, I think after 2 weeks, we plan to go back in person if things are back to normal, sort of normal. This is a new and completely very exciting class for all of us. We are for the first time offering EECS 251B, which is a course on advanced digital circuits and systems. It is a follow-on course, entirely graduate course for that follows EECS 151 251A, and is intended for graduate students, our PhD students, fifth-year masters, and MN students, as well as advanced undergrads who are interested in building complex digital systems, as well as an understanding how they actually work and what are the principles of building complex systems. The instructors for the course are myself. My name is Bora Nikolic. Also, we have Vladimir Stojanovic and Sofia Shao. The TA for the class is Eric Anderson. We will, I'll just basically say that I'll be holding office hours on Thursdays from 11 to 12, or by an appointment. Most of you got to know me and know how to reach me. Physical location will be Corey Courtyard for my office hours. Some of you have also been used to do that, to doing that. And at some point, if it is raining, we'll find some place where it is not raining, like my office. I'll let the other instructors introduce themselves. Vladimir. Are you there? Or Sophia?
Sure. Good morning, everyone. Great to see you here. I'm Sophia Shao. I'm also a faculty member here at UC Berkeley. I'm very excited about this course. I think it's a very interesting course that brings students and also faculty of different background to actually build very complex, but also super useful modern system. So my office hour is actually Tuesday today. So if you have any questions, feel free to reach out to me. It will be on Zoom for at least for the first couple of weeks, and we'll see whether it will be in Corey Courtyard or in my office. But I'm looking forward to interacting with all of you. Mm-hmm.
And the TA for the class is Eric. Eric has been at Berkeley for a while and has taken a whole bunch of classes and has put on a heroic effort over the last day or so to regain various spaces in the virtual world to host the web page. You'll be also holding an office hour. Eric, did you want to introduce yourself?
Sure, yeah. So good morning, everyone. I'm Eric. I'm a third-year PhD student here at Berkeley, and I work with Vladimir Stojanovic and Ming Wu doing circuit design for MEMS optical switches. So excited for this class and excited to meet everyone. Thanks.
Very exciting research topic too. All right, so getting into this, this class aims to convey the knowledge of how do we build systems on a chip. It has two essential facets to it. One is, how do we do that? And then the other one is why we do things in a particular way. The lectures are going to be dealing with how and what, explaining the principles of how do we design things in a particular way? How do we build these complex things? How do we make them deliver maximum performance with limited power consumption, and so on? And then we'll have a number of labs that will essentially guide you through how do we do that by using commercial tools. Of course, we can't cover everything. There will be a number of reading assignments that will supplement both the labs and the lectures, and we'll try to guide them through those. One thing to keep in mind, we'll try to target a broad range of applications, from edge computing to data centers. And we'll always keep an eye on where is the technology going over the next decade or so. We'll try to be both qualitative and quantitative, and try to develop reasoning on how things are done, and we'll very quickly establish the fact that this is the entire design space of trade-offs, and these trade-offs, you as a designer will need to make them by using some kind of an analysis. We'll be going through a lot of papers in this course, and we'll be using them to highlight what are the enabling techniques and how they have been deployed in different scenarios. What you'll find out to supplement what is published in papers, sometimes we'll be using public sources, other public sources. We'll not be talking about anything proprietary in this class, but you'll find out that occasionally we'll point to something that is reverse engineering report or something like that. We'll try to shine a light on how something is actually being done in practice, even though it is not completely documented in publications. However, our ground truth will still be papers. We'll talk a little bit more about that in a second. When contrasting 251A and 251B, we'll see that 251A was, and most of you have taken it very recently, either with Sophia or with myself, it is kind of a drill course. We set on an assigned goal that we would like to build a RISC-V processor core, and we go, we go at very fast pace from start to the end, and we accomplish that. By using modern tools and implement that in an ASIC methodology or an FPGA methodology. But the course is fairly rigid. There is very little space for exploration. We just basically sprint for 14 weeks from start to the finish. And we essentially set that up as one-way avenue. We do give a little bit of freedom in the end to do some optimizations on the design, but it's a set of strict goals and design rules, and we expect everybody to execute that. 251B is more of a flexible class. We would like to explore things. We would like to understand what are the technology possibilities and what are the limitations. Where is the technology going and what we might be able to do in a few years that we are not able to do today. We barely touched on a transistor model. We'll spend about a week on understanding transistor models here, and there'll be some equations that'll help us analyze how things work, how and why are, say, standard cells built in a particular way, and why do flip-flops work the way they should. We really did not realize where the constraints came from in 151. instructors and the TA somehow set some kind of a set of goals, but here we will try to understand that there is a power constraint and there is a performance constraint, and they can be traded for each other. And these will, by setting different kinds of constraints, we will, we'll end up exploring a different set of curves and trade-offs in different design spaces, say, building a cloud machine versus a cell phone. We will learn quite a few more advanced design techniques. You'll find out that 95% of the design that is being done nowadays is plain standard CMOS built out of a library of standard cells. But what makes the difference in high performance or low power are these specialized techniques that differentiate really spectacular circuits from vanilla kind of ones. And then so the emphasis there would be to understand those and when to make a judicious call to deploy them. It is something that generally a graduate student from a well-established program like Berkeley would be in charge of doing. We'll keep an outlook on where the things are going, and the project that we are going to explore is going to be completely open-ended. You are going to be in charge of it. So what we are going to spring 2022, I still have not flipped my calendar to 2022. So we are going to be talking, the whole class will be in the context of building an SoC. And since there is so much talk about where the technology is going these days, we're going to spend a couple of lectures studying that. Where is the technology now, how we got to it, and where is it going? Then we'll spend a bit of a time on process variations, because that is one thing that we haven't talked about yet in our previous classes. This is something that really affects how we get these parametric yields in volume products. And that will matter for your careers as aspiring designers. We'll make the design robust such that we actually can achieve those parametric yields. We'll spend some time on memory, trying to study how do we architecturally put memory in the context of an SoC, and then how do we execute that circuit design, memory circuit design, such that it is robust to process variations. A third of a class is going to be spent on energy efficiency, and we're going to spend quite a bit of a time on that. And we'll close in the end with power management, with fairly sophisticated techniques that are being now used in systems on a chip to make sure that the performance is maximized under power constraints. This is a new course, and we actually don't know exactly what we are going to do. Things will change, but we are going to start off with presenting you an SoC design template, and we are going to get everybody to run through a couple of labs to build an SoC instance. We're going to spend some time covering languages that we haven't covered in 151. Specifically, we're going to cover Chisel that we used in research here, and some aspects of system Verilog. One thing to keep in mind, there is no way to teach the entire system Verilog, but there are some very useful features of system Verilog that are needed for verification. And given that most of you are going to encounter that in industry, let's be done with, let's cover that now such that it is out of the way. We'll spend, as I mentioned earlier, we'll talk about the current technologies and the outlook of technologies. Where are we going with FinFETs and beyond FinFETs? And what do we need to do before we get to quantum? And what are our chances before we get to some really exotic and different things? We'll talk about models. We'll start with transistors. We'll build the gates out of that. And then we'll build standard cells out of them, talk about the abstraction layers, and then eventually talk about the system level modeling. We'll spend some time designing for performance. Typically, we are going to revisit this timing thing and revisit it in the context of using latches in addition to flip-flops, something that we kind of just mentioned in 151, 251A, but you'll find some of those in practical designs, and you need to be aware of that because somebody has to do it. We'll spend some time on SRAM, perhaps not the entire 2.5 weeks, maybe about 2 weeks. We may even have a guest lecture on that, because half of the silicon die nowadays is some kind of an SRAM, and we need to make sure that it works. It doesn't work just magically. You just plop down a few tens of megabytes of cache and it works. Then probably the largest module that we have will be on energy efficiency, and then we'll tie that to the clock and power distribution. We plan to run the final exam in the last week of classes. We plan to run this class in a little more relaxed way than what you've seen in 151, for example. We don't have assignments every week. We do plan to assign something approximately every other week early on, maybe a little bit more frequent early on, and more sparsed out towards the end. There'll be about 5 assignments with embedded labs. These labs are more involved than what you've seen in 251A, but shouldn't take a lot more time. So put it this way, if you've taken an ASIC lab in 251A, our lab 3 here will summarize all of those labs in one lab. So you'll rerun through them. There are not as many embedded questions. And the idea here is to make sure that everybody has a design methodology that they can use in this class, but also they can use it in research. What we have found out is using a class to teach a whole bunch of graduate students a common design methodology is a lot better than teaching everybody one-on-one by using informal channels, from a student to a student. The second thing that we'll have about 4 quizzes that will follow the first 4 assignments. We probably won't have a quiz after the last assignment. And the reason for that is to make sure that people are current with the materials that we cover in the class. If we don't do that and we don't have a midterm, then this class turns into an unfortunate cramming 48 hours before the final, and that's not good. So this just gives them additional motivation to keep up with the materials. The big part here is going to be essentially a term long or 3/4 term long design project. That is a major part of the grade. And this year, in future years, this may change, but we'll let you pick your own topic. And we are going to give you approximately a month to do that until after ISSCC. The second phase of the project is the paper study. We'll give you about 4 weeks to do that. And we would like you to pick about, let's say, 4 or 5 papers that are addressing that topic that are recent. That's why we are picking the deadline after ISSCC to choose a topic such that you know what is current, and pick the most relevant and recent papers for that. And then after the spring break, in the last 5 weeks, 5 or 6 weeks, you are going to prove that study or disprove it through a design. And we're going to have a presentation on the first day of the RRR week. We're going to have a final exam, and we're going to do it in class on Thursday, April the 28th. We do, so this is tentative. We typically do this to try to avoid collisions with other classes. Typically, students do get very stressed out over 240B final. And the way how these classes are scheduled, it turns out that those two finals end up being based on how the registrar does them, schedules them on the same day back to back, which is unnecessary stress for our grad students. So to make sure that these two are spaced out, and the word out is that this exam is a little easier than 240B exam, we get it out of the way first. Or in the last week of classes in hour and 20 minutes. The other collision that we have is with 252, which is running in exact, some students are taking this class in 252, and 252 is running in exact same time slot, which means that it will have a final. If it has it, it typically doesn't have it at exactly the same time. But I believe 252 is going to have two midterms. We'll check that, and the second midterm is going to be the week before. So hopefully this is clear, and you have a few days for studying every single one of these, for every one of these classes. One thing to mention here, there is clearly no textbook. Anything that has been published out there is outdated by the time that it gets published, unless it's a very recent paper. Some parts of the class will follow a book that is essentially a collection of slides that we have used some decade ago, or more than a decade ago, that Jan Rubai published as Low Power Design Essentials. And you don't need to buy that book. It's available to download from Springer Link. There are a few other books that are relevant, that will sometimes point to. There is one that is interesting, that is kind of a theoretical treatise of the VLSI design methodology by Tom Dillinger. I'll sometimes refer to it. And the one that was a real good match to this course 20 years ago, which was the Chandrakasan, Bohill, and Fox book, Design of High Performance Microprocessor Circuits. But unfortunately, it's 20 years old, so there is a small amount of relevant stuff that is left in there. In particular, we are going to touch on timing from that book. And the other books that we use in 151 are good as references as well. The web page, as it gets populated, will get some of the background material. Typically, we'll be linking some papers from IEEE Explore and other resources. Everybody should know by now, typically graduate students, PhD students do know that, and living in a semi-virtual environment, we have all learned that we can use, in order to use the library, we need to go through the VPN or set up a library proxy or use a VPN. So if you don't know how to do that, do it now. You need it anyway to run the labs. I'll be putting class notes and slides on the website, and they're already up on the website. There is a lot of reading that we do in this class. Sometimes you'll find out that it's way too much. We will limit the assigned reading to 1 or 2 papers per lecture. Now, keep in mind that sometimes this may be misleading. If you look at these papers from ISSCC or VLSI, they look like 2 pages, and they're really 2 pages, but those are really dense 2 pages where every sentence has some kind of a weight. it would be great if you could read them before the class, and we'll post these reading assignments beforehand. Sometimes we'll be, more commonly we'll put journal papers as assigned reading because they're helpful. They explain things in a bit more of a detail. We'll give some recommended reading and background materials. We don't expect them you to read them unless you have a project that you're picked in that space, and then you should definitely read all of those, because if we read them, we should read them before you do your project. There can be a lot of them, and we'll try to color code them as optional. As abbreviations of reading sources, there will be journal solid-state circuits as JSSC. It will be International Solid-State Circuits Conference, ISSCC, Symposium on VLSI Technology and Circuits, which will be abbreviated as VLSI, and other ones that we have we'll try to spell out because they are not as common. You can pick whatever you like to do as a project. Good topics could be something in memories, power management, clocking, building SoC components, and you do want to have every single one of these projects to have some relevance to the SoC that we'll have in lab 1. So it can be a small piece, or it can be a building block, or it can be something that can be used to manage the entire SoC. Feel free to discuss it with all the instructors. We like to run projects as two-person teams. We would like to avoid single-person projects if possible, so team up now. If there are 3 members of a team, then that should be a larger project. We can also explore, if you're in both 290C and 252, we can explore something that is a larger project that strides multiple classes. Do let us know. We are open to discussing things. We'll give a few more details in the next week on how does the project look like. When we talk about the tools, we do want to keep things out of the NDA space. So it has to be something that is accessible without having to sign access to proprietary things. So we are going to use a 7-nanometer predictive model from ASAP7, the same library that we have used in 251A, and with its associate complete design kit. You guys have seen this before. That class, that design kit is largely complete. Memories are just very thick. Totally fine project is to try to reduce the amount of thickness in those memories, as a hint here. Some things can be related to Intel 16 if you're enrolled in 290C, and I know that a number of students are. But keep in mind that nothing that is proprietary in Intel 16 process can leak over to the class, because if not everybody in the class is under the NDA, and we have to keep proprietary things proprietary. Cadence and synopsis are available instructional servers, so they are good for building systems, including the Berkeley's open source flows and tools. Our labs will feature Chipyard and Hammer. If you have taken 251A, you have seen a glimpse of Hammer. You're going to see a little more of Hammer this time. That is an abstraction tool that we use to interface to the commercial CAD tools in a friendlier way manner. And then we can use other open source tools and models as needed. We had to start with Zoom, so we'll post the recorded things, but our focus will be on interactive lectures. So I really would like to avoid the situation where that we had in 251A, where out of 100 plus people, 15 or 20 would show up in the audience later on. And if you're running this from home, it is probably a higher reliability. You're going to get a reasonable recording. Than if we are recording it in Corey. So please do come to classes if you can, if you don't have some condition that prevents you from coming to a class. And we do want a lot of discussion in this class. As you know, we have had good discussion. Those of you that took 251A recently had a good discussion in classes. We would like that to continue, and being interactive in person is hopefully gonna help with that. However, we'll post the recordings if we get them. Now it's a good time to pause to allow for any questions you may have. So I see some questions in chat. Yeah. 251 LB is completely different class. By the way, it's a good idea, since we are on Zoom, to give a break from time to time. But go ahead, any questions? And feel free to ask them through chat. We have Eric and Sophia answering when I'm talking, and from the sound of my voice, you probably can hear who is supposed to be in quarantine now, actually. The question is, will the lecture slides be available? Yes, they'll be on the website. They're already on the website, and I'll be posting annotated ones, because when I teach, and I know how Sophia does it, and Vladimir as well, we all scribble a lot more in this class over our slides. Those of you that had 151 with me or Sophia recently have seen some scribbling. I scribble a lot more in this class, so annotated slides are mandatory. Will the course be covered in INC prelim? Yes, this course will replace 241B in prelim requirements. The question, is there an issue if your partner is not enrolled in 290? Yes, yeah, you can have a partner. You cannot have you cannot use 290 project unless both of you are enrolled in the class, in that class, and have access to it. Right. I mean, that's a very special class, and requires access to proprietary technology. In this class, this is a general class where we can't have that kind of restriction. All right. All right, I'll give you a 30-second break, and then we'll continue with the trends and challenges in digital circuits and systems. All right, moving on. We're going to post some of this readings. You can skimmed through most of it. We are assigning the chapter 1 introduction from Rabai. You can actually, or we should probably move that over. But there are two papers that I particularly like. I like Gordon Moore's ISSC keynote from 2003, and you can see how relevant it is to up to today, even though it was done 19 years ago. And there is also a very good keynote by T.C. Chen from ISSC keynote in 2006 that is very much worth reading on the outlook that turned out to be quite right from 15 years ago. And there are many other keynotes out there that turned out not to be as right as those two. There are a few other interesting papers that are worth reading if you're interested in this, particularly the chapter 1 from historical perspective, the chapter 1 in the book that we used before from Chandrakasan, Bowhill and Fox that was written by Edmondson was really a great coverage on how does physical technology impact architecture. However, it is not relevant. It was relevant for water micron technologies back then. In a nutshell, what we would like to do here is to cover design decisions that are needed to make a modern SoC. What we can see, for example, is if you take what we teach in, say, 151 are some of the techniques needed to design one of these, not even something smaller than the energy efficient CPU. Actually, what you'll find out, there are all kinds of little control CPUs that you'll find out around IOs or something like that. They'll be somewhere over there that you'll find them. And that's basically 151 project. Now we need to somehow scale that up by 1,000 times or 10,000 times and use a lot bigger design team to design something much more complex, like what we have here in Apple A14 or M1. I think this is a picture of M1. So there are design decisions that are made around designing these high performance cores and energy efficient cores. We're going to study how different those are from each other and why they're different from each other. We won't spend time on a GPU. If we get the chance, we might get a guest lecture on one of those. We won't spend time on the next big chunk over here is the NPU. Professor Sophia teaches a whole class on how you design those kind of things when she has cycles. So that, that's yet another big topic. We may mention it, so Sophia may mention that in some of the lectures, but we're not going to go in depth with that. One of the big things that we are going to try to spend time on is to try to understand other components, especially through the project, through the SoC template. What other components are needed in this SoC, and how do we build interconnects for these kind of systems. A good chunk of a class will be on relatively low level design of clocking, memory, and power management. In particular, what you'll find out, all these regular arrays on this die contribute to probably about 50% of the die area. And if you look at Intel processor, high-end processors, more than 50% of the die are memory arrays. We'll spend some time on understanding what does it take to build these arrays nowadays. And a big chunk will be in figuring out, for example, for a processor of a class like this, how do we get it to, on the average, consume only a couple of watts, while at the maximum, at the peak, is totally capable of dissipating 20 or more watts? How do we manage it such that it fits within the power envelope that it is allotted in a small form factor computer? And that is probably one of the biggest challenges of today's design. We'll try to shine some light on that. One thing that we do want to put in a perspective is, where is the technology going? And here is an interesting plot and another interesting keynote from Morris Chang, the founder of TSMC, that he gave at ISSCC in 2007, where he was trying to put the semiconductor industry in the world's in the perspective of where does it fit in the world. So semiconductor industry was going through very rapid growth from its inception up to the 60s, where it had a 100% annual growth rate. Then, as a new industry and relatively small industry, it was growing at a 16% growth rate. And then in the early 2000s, he noticed that it scaled down to about 6%. These percentages were actually larger than 6% lately. This change in slope had to happen because semiconductor industry is becoming more mature and is becoming a larger fraction of the gross world product. So somebody made a prediction back then around in the early 2000s. I think it was Morris Chang. By if it continued growing at that rate, by the age of 2050, the entire world product would be semiconductors, which is clearly not possible because we do need shelter, food, and clothing. We need to allocate some amount of our budget to that. This is showing also this graph that we have gotten from public sources is showing a wild ride that semiconductor industry has been going through over the past few decades. Growth rate, if you plot it, is actually faster than 6% still, because semiconductors have been getting into other aspects of life, meaning into they're much more prevalent in our housing, in our clothing, in our transportation. We are not eating semiconductors yet, but they do, they're a lot more spread through our supply chains, including the food supply chains. But it is an industry that is turbulent and that is going through these rapid jumps of 20% from a year to year, and then declines, sudden declines out of nowhere by 5 or 10%. Would anybody like to share an opinion? Why did the industry dip down from 2018 to 2019 by almost 10%? We are unaware of a worldwide crisis, are we? That happened 3 years ago. Why did the semiconductor industry shrink? Well, that was kind of a compensation to what has happened to this, sudden growth by 20% that happened from 2016 to 2017. Anybody knows what might have happened then? Gosh, you guys are really quiet. Well,
the increase in memory price, or
exactly. The changes here that have happened are because of the turbulent DRAM pricing. So there was a DRAM shortage from in 2017, then that increased the prices. What caused the DRAM shortage back then? Crypto mining was, that was the onset of crypto mining. So suddenly people are buying DRAM. At the same time, that was one of the onsets of people trying to do machine learning, and that also got compounded with an extended downtime of one of the factories that went through, I believe, a fire. Then what happened in 2019? Well, the DRAM price went down because people built up capacity, and suddenly there was at the same time it became not as economical to mine cryptocurrencies, and the DRAM price went down. Now, because of the current conditions, we had a rapid growth from 2020 to 2021. And this projection that is still for 2022 is possibly pessimistic. It is, the latest projections are showing that the sales are going to exceed $650 billion. So this is a very rapid growth. Is projected because you might have noticed is that because of the shortages, the prices have gone up. That likely means that a couple of years down the road, when the capacity catches up, the prices are going to go down and market is going to shrink. And then it'll continue going up. In most cases, it does not affect us as designers. Most people who are in this space, unless they work for a DRAM provider, did not even notice any of these turbulences. The things just continued going up and up. But the point here is, if you're looking at this rate of a good fraction of $1 trillion, semiconductors are about 1% of the current gross world product. There is still room to grow before it becomes a very large percentage of it, and that's what is going to be the trend for the next few decades. So what is the largest part of the semiconductor industry? Is the memory, and memory prices are the most volatile. Traditionally have been and continue to be that way. So that's why we are seeing these turbulences. And most of us are not in the memory business, typically DRAM and flash business. And we are generally not affected by that kind of, but by the price variations that we are seeing there. A few notes about Moore's law. You've heard about it probably 1,000 times, and so why are they talking about Moore's law again? One thing is we want to set the record straight, that because there is still a lot of speculation, and there are a lot of articles about that. So when you look at Gordon Moore's original article, he noted that the number of transistors on a chip would double every 12 months. That was back in 1965. And then he ended up correcting that to 18 months. and then soon after that to 24 months in 1975. So essentially, what does it mean, this doubling its effectiveness every 24 months? Meant that the number of components that can be integrated on one chip will be doubling every 2 years. That indeed held up, and you can see that this is a very bold prediction that was an extrapolation of 5 data points that he had early on. And there are interesting articles, that have been tracing down how did he pick these 5 data points, because there are other data points out there, that there are other chips that were in there. But the prediction after the correction around 1975 held up for a long time. If we look at what is currently happening around 2020, is that there is a notable slowdown in recent years. We are definitely off that doubling the number of components every 2 years, and it is even more evident over since 2020. I used to plot these things, but really didn't collect the data that recently. So it is clear that the Moore's law is not like what it used to be, but the Moore's law over its mid 40 years was really different than what we have had in the early 10 years. So does this mean that this is some kind of an end of the industry? What does this mean, that the Moore's law is not going to continue? Well, semiconductor industry is going to continue improving its effectiveness. It is not going to be as effective as it has been in the past. We are not going to see as many components, but you're going to see integration of higher complexities on one chip. Towards the end of the original Moore's article, he mentions a couple of more things. One, he speculates that all these transistors may be used for building phased arrays, which is kind of interesting. We did not end up building phased arrays, although there are some people in our research that are using a lot of silicon area to build phased arrays. But he also mentions multi-chip modules, that when we run out of a state on one chip, we can spread it out to multiple chips. And that is one of the big trends that we see nowadays. Everything that is behind that is the cost. What rules the Moore's law, which is not any kind of physical law, is the fact that transistors are becoming cheaper and cheaper. And current cost of a transistor, each transistor costs 1 billionth of a dollar. So from that perspective, you can consider each transistor being free. We'll talk about the limitation and where is the fallacy in that. People have had quite a bit of a concern of what's going to happen when Moore's law runs out, and what is going to replace CMOS technology, which was the dominant driver. There has been a number of devices that came out that this spintronic storage is not showing up on my slide, but we have had millipedes that almost reach commercial deployment in mass storage. There is a number of spintronic devices that are out there. There are nanomechanics, nano relays. A good number of dissertations have been written over here about that. We have seen nanotubes and nanowires, and molecular electronics show up, and quantum is something that is very popular. But these have been around. I mean, this is TC Chen's keynote from 15 years ago, and we really have not seen these in volume production. So what he predicted back then turned out, and I mentioned that as a good paper to read. What he predicted back then was incredibly accurate. So he outlined for a few plans for the industry, and the industry has been really good at executing that. So the plan A is to extend the silicon CMOS. So the big threat that was looming around 2006, around his keynote, was the gate leakage in transistors and generally drain leakage, all kinds of leakages that we had in the technology, and something had to be done. He correctly predicted that we needed to change the transistor structure. The two topologies that were proposed from Berkeley in these pictures were the FinFET and fully depleted SI or ultra thin body SI. Both of them have seen commercialization soon after that, soon after 2010. So that's how these things moved from research to development. Plan B is, as we hit the limits of many of these devices, is to try to integrate whatever we can and increase densities in what can in systems, subsystems that can that are amenable to density increases, but don't do it everywhere. And mix and match things, implement them in optimal technologies for that particular application. This is the idea of 2.5D and 3D integration that is very much popular now. Then the idea was, way out there in R&D around now, is to try to explore post silicon CMOS options. So at some point, basically the size, minimum size of a functional CMOS transistor is going to become impractical to implement. And the idea was to try to explore different materials that can act as semiconductors. And then very deep down, there is a plan Q to explore quantum. Quantum is really popular, and it is becoming much more practical now, but not in every aspect. So we are going to see one of the things that is going to happen with subsystem integration is domain specialization. We're going to spend some time in this class talking about domain specialization. And what we'll see, quantum may be interesting for certain domains. It hasn't made its way into the lecture plan yet, but maybe in a year or two, we may have to have a lecture on quantum. When we are talking about CMOS, this is another plot that is very important to keep in mind. When we talk about the scaling, scaling has been attributed to all kinds of things. Typically, people have been associating scaling with the minimum gate length in a transistor as a representative of a minimum feature size for the technology. But that has been very, very misleading, and it is very particularly misleading nowadays. We're going to have a lecture that is going to dive a little bit more into this in about 2 weeks. But here is the gist of it. Nominally, gate lengths have been tracking the technology scaling. So we went from a 250 nanometer technology to 180 nanometers, to 130 nanometers, 90, 65, 45, 32, and so on. but the gate lengths up to 250 nanometers were actually matching the feature sizes. But then a really aggressive drive for speed in microprocessors as a driving application of that time, of late 90s and early 2000s, led the technology developers to increase the speed. So the speed of microprocessors was jacked up by microarchitectural changes, by really, really exotic circuit design, but also by technology enhancements. These technology enhancements essentially meant that the technology was trimming down these gates to lengths that were below what was minimally printable in a particular technology. So, for example, 130 nanometer technologies featured 70 nanometer gate lengths. 65 nanometer technologies had 35 nanometer gate lengths. And then things slow down because really short. And the way how they did it, they basically trimmed the gate through by so-called ashing process. So they print a nominal gate size and then they trim it down. They grind it down a bit. But that became impractical around 45 nanometer technology, and the gate lengths remained constant at around 30 nanometers for a while. The changes in material structure enabled further scaling of gate lengths to about 20 nanometers. And then down at 14 nanometers and below, the gate length, the physical gate length, is longer than the nominal feature size. How is that possible? How does this make sense? What are the gate lengths that we see, say, in these N5 or 5 nanometer technologies? Does anybody know? What's the gate length in 16 nanometer technology?
I think for 16 nanometers, the gate length is about 5 nanometers.
No, it's about, I believe, what you have seen from the reports, it's about 20 or 19 is what people have been measuring. It has been relatively constant. So when we go down to N5 node, it goes to about 15 or 16 nanometers. Kind of interesting. How does that make sense? Well, one thing that we'll see relatively soon, these technologies, N5 and N3 are mostly marketing names. They kind of correspond to overall density that is close to what should have been Moore's law technology that corresponds to that node, but not quite. We'll take a look at that in 2 weeks. The other thing that has been very notable over the past 15, 20 years is that in every node, the technology has had a significant change, that the transistors have changed. So, back when I was a student, when I was taking a class like this, there were very limited, there was a very limited number of changes that happened at the transistor level. They were just getting smaller. But then around 65 nanometers, some fairly dramatic things started happening. We are going to talk a little bit about those. For example, first, what we have seen, introduction of a strained silicon in 65. Then 45 was a big dramatic step of introduction of high-K metal gates, in addition to the strain. there was no dramatic change except in the way how this high K metal gate was made down to 32 at 28 nanometers. And then there was a dramatic step from there. Intel has introduced FinFETs in 2022. ST has introduced fully depleted SOI, or extremely thin body transistors in around the same time in 28 nanometer technologies. And if you look at the FinFETs now, the shape of a FinFET has changed in every technology node. They unfortunately stopped plotting these nice SCM pictures as they've done for early generations of FinFETs. So we only see these, not these blurry reverse engineering reports, but we see that the change of a shape of a fin towards what marketing guys are now calling super fins essentially continues, that we are seeing taller and skinnier FinFETs. This is going to continue changing, and we are going to see the impact of that as we go along. The other thing to keep in mind is that, again, when I was a grad student, there was, you get your technology, say, 0.35 micron technology or 0.5 micron technology, and there was basically one type of a transistor. May get an IO transistor in addition to that, but that was it. There was just one transistor and one NMOS and one PMOS, and you just run with that. Now, there are many flavors of a transistor. So what we'll find out is that in, say, 32 nanometers, in this Intel's paper, you'll find out that there are at least 3 different types of transistors. There are so-called high performance or standard performance, HP or SP, and low power transistors, LP. And then there are high voltage IOs. The transistors, HP, SP, or LP, are physically different from each other. For example, they have different gate length. These things were, changing technology from a node to a node, or picking different flavors of devices within a node or within a particular technology flavor looked really, really scary at some point. Because we have this huge design stack that is built on top of that. And if you change a fundamental thing like a transistor, wouldn't that topple the whole thing? Wouldn't the whole thing collapse? But the point here is that the way how we model this and how we built the abstractions in the design stack enabled us to do this, that we can swap out the transistor and the rest of our methodology stays the same. It is essentially built in the abstraction of the standard cells and the modules and, say, memory blocks. Also, interestingly, the models for transistor behavior have not changed in recent technologies. They're not going to change going forward. That's why we're going to outline them at some point. Going forward, when we are looking at this 5 nanometer node, you will see this soup of different transistor flavors. So on the blue, points on the graph are N7 transistors from TSMC. The red and black ones are different versions, 2 different versions of N5. N7 is that technology that is equivalent to what would have been Moore's Law 7 nanometer technology. And N5 is what is the equivalent of a Moore's Law 5 nanometer technology. What you're seeing here is a plot of the standby power, what is the leakage power essentially in microwatts for a particular benchmark block versus the speed in gigahertz. And there is not, as you can see here, there is not even these are unlabeled graphs, and there is not even an order of magnitude on them. And you can take a look at and compare to these, 25 and 15% errors to get a scale of it. But what you're seeing here is essentially that there are so many different flavors of a technology. 1, 2, 3. Oops, did not mean to do this. 1, 2, 3, 4, 5, 6, 7, 8, 9 different flavors in N5. As a designer, you don't get to pick all of them. You pick 2 or 3, and we're going to try to talk about the decisions that lead to picking them. But these essentially are extremely low VT or ultra low VT, and then going down to low leakage and so on. Industry has been also getting used to these changes in how Moore's law affects it over time. So this is a great plot of that Lisa Su has shared at Hot Chips, her Hot Chips 19 keynote, where she has shown what has led to increases in performance. So process technology has contributed to 40%, and that is great. We are likely going to see less of the gains through technology itself going forward, but it's not going to disappear. What we have seen, the designers have figured out how to live with higher temperatures, so higher thermal design, how to build larger die sizes. Micro architects have been busy doing their stuff, re-architecting the systems. And then power management was a huge component, and it is believed that is going to be also a very big component going forward. And then, the software became more efficient through compilers. One thing that is a bit scary over here is the scaling of the cost. So what she's plotting here is that going down from a node to a node, from 90 nanometers to 65, 65 to 45, the cost of making a module or scaling transistors has been going down by a half. But that has slowed down in 14 and 10, 7 nanometer technologies. There has been an improvement down by deployment of EUV going to 5 nanometer technologies. But transistors, the point here, even though the scaling continues, transistors are not getting that much cheaper as they were before. So one of the big questions then is, what do we do next? So this is a plot of power and performance trends that is trying to highlight what we have seen before. Let me try to get the laser pointer working. So this is a plot. The top plot is a plot of Moore's law up to roughly 2010, and it's continued, although not. We're seeing some flattening after 2020. Performance used to come out of the frequency, but the frequency of microprocessors stopped increasing after 2004, roughly, because the leakage and the power became unacceptable. The frequency was limited by the power, and that's why we saw flattening of the of the performance back then. The way to get more performance was achieved by going parallel. So we saw the increase of parallel processors integrated on the same die, and parallel lab performance continued going up. Now that is going to flatten out, and many have pointed to that. So what do we do next? The key thing is we do domain specialization. So building things that are specialized to particular applications is more efficient way of getting performance out of a limited power budget. And that's the name of the game. And that's why why everybody is hiring designers at the moment to build their custom solutions for for a particular domain. Now, one of the big challenges here is developing a new product, a leading product in a leading technology node is really expensive. And these NRE costs, non-recurring engineering costs, have been nearly doubling in every technology node. This is not exactly true, and it really affects a limited number of products. But we'll try to dismantle this throughout the class and understand which products are actually affected by this and which ones are not. So as we go through this class, we are going to try to navigate some of these major roadblocks. We're going to try to see how to navigate complexity. And there'll be a focus of many of our labs. Try to build these SoCs in a relatively inexpensive way, inexpensive labor wise. How do we break down products such that we can build them out of chiplets? And we'll be mentioning some of that. And then we would like also to know what do we use all transistors for? At the moment, we use majority of the transistors to build SRAM and caches. There perhaps may be a better use for them. It takes, the second thing is how do we handle this increasing NRE in the light of domain specialization? And that is something that is a challenge, and we'll need to figure out how to do that. We again, in research, we have methodologies that are getting around that, and you're going to see a glimpse of that through our labs. Because as graduate students, we are really understaffed here. I mean, you get to design your own chip, and you don't get a whole design team to work with you. One big thing, power has become a limiting factor in the early 2000s, and it is still a big limiting factor, which meant the end of frequency scaling, and we need to deal with power limitations and leakages. Robustness has been a problem, has been handled over the past few years, but introduction of some of these new technologies require us to come up with new solutions. We'll cover some of those in the class, and they need to be exposed to a designer. And then interconnect simply doesn't scale like it used to scale before. That is it. Do you have any questions? And my voice held up this time. We'll see how it holds up over the next few lectures. The next lecture will introduce our research tool, which is called the Chipyard, as an SoC design template. And we are going to have a lab that we are going to release this week that are going to get you to build your own SoC by using Chipyard. Any questions? If there are no questions, we can wrap it up. Thank you very much, and looking forward to a very exciting class. Thanks all.